But if we need to transmit at higher rates, bit rates, or we need to transmit farther, that is at the same bit rate supported by twisted pair, but we need to transmit in longer distances. We need to use another media, and that media is the optical fiber. And only in order to pay attention to the vocabulary, fiber written with F-I-B-R-E is in the English way. Is the English word of fiber, and fiber written in that way is the American way of writing fiber. But we could use any of those words to talk about the fibers. We are talking about logically optical fibers. Then only to clarify, the advantages of the optical fibers are mainly the high transmission capacity compared with the twisted pair cables, low susceptibility to electromagnetic interference because it's not electrical, it's optical. And there are other advantages like potential separation between transmitter and receiver. That is, when we talk about potential, is we talk about the voltage that is electrically isolated. There is an electrical isolation between the endpoints. Between the transmitter and receiver. That is, we don't need a ground loop between those devices. Long distances between repeaters over 300 kilometers is possible, typically for C cables. Large production lengths are possible, therefore greater distance between couplings, therefore fewer couplings, therefore fewer installation errors. That is a lot of advantages. Highly resistant to eye dropping, short circuit free because no spark formation is possible. And that is important in areas where there is a risk of explosion. Lightweight, highly flexible, lighter equipment, easier handling, less volume for shipping, smaller cable reels, lighter trailers, smaller winches, smaller dimensions, smaller cable diameter, more effective utilization of cable ducts. That's in fact a lot of advantages related with the the installation, the transport, etc. There are no corrosion of fibers. Another advantage, very important in some cases. Unlimited material availability. That is, this component is available in nearly limitless supply. And there are some disadvantages. We need to respect particular installation technology, and that is very expensive. We need to apply high level of precision in order to install and maintain that kind of installations. And sophisticated devices are necessary to transmit and receive and operate. Well, The optical fiber. The optical fiber in optical transmission, an effect of total internal reflection is desired. That is, we need to use the fiber as a guided ray and a guided ray device. We'll talk about the guided ray modes. That is the rays, the light rays that are propagated within the core of the fiber. This effect occurs if two transparent media are arranged one above the other. The external medium must be better in terms of refraction index than the internal one. The combination of glass and air would also fulfill this condition. However, one achieves more favorable characteristics with two almost equally good types of glass. An optical fiber consists of the following components: the core, the information carrying glass. This is the core. The cladding, a slightly better glass, that is the index, the refraction index of the core is higher than the refraction index of the cladding, and that permits a better behavior of the fiber in order to maintain the ray modes within the core. All the ray modes that are propagating within the core will remain within the core because of all the rays will arrive to this interface with an angle that is higher than the critical angle. We will see this later. Wavelength in the field of optical telecommunications, the wavelength lambda, represented by this letter lambda, is indicated instead of the frequency. Visible light occupies the wavelength range from 380 nanometers violet to 780 nanometers, that is red, the color red. The frequency which meets the red wavelength range but is no longer visible is called the infrared branch, IR. One differentiates between the near, medium, remote, and very remote IR ranges. Optical telecommunications use the near IR range around the wavelength 1 micrometer, that is 1000 nanometers. This corresponds to a frequency in the order of magnitude of hundreds of terahertz. This is the equation to convert the wavelength into frequency. Typically, the frequency is equal to the speed of the light divided by the wavelength of the beam. For instance, for this wavelength of 1 micrometer, then if we apply this equation, we will see that the frequency is 300 terahertz. Well, propagation velocity and refraction index. In air or vacuum, light has a propagation velocity of 300,000 kilometers per second. If light enters a different transparent medium, its velocity changes, is reduced. The change in the velocity corresponds to the ratio with which the medium is denser than air. The factor by which a material is denser than air is called the refraction index and designated with N. It indicates how many times denser than air a medium is. Remember that the refraction index of air or vacuum is 1, is the lowest density or highest light velocity or speed. All other transparent media are denser, that is, with a refraction index higher than 1. The propagation velocity of light determines transit time of the pulses from the transmitter to the receiver traveling into the core of the fiber decreases in direct relation to the increase in density. A glass has an index of refraction N of approximately 1.5. However, the refraction factor or refraction index of a material is dependent on the particular wavelength. That is wavelength dependent. And here we are a graph that shows the variation of the refraction index of the glass based on the wavelength of the light. Silica glass, the material for fibers used in today's cables, is exclusively silica glass. The Earth's crust consists of 26% silicon. Quartz appears in its pure crystalline form as rock crystal, for example. Silica glass, on the other hand, is an amorphous, solidified, molten mass. It has no melting point, but becomes increasingly soft at high temperatures and vaporizes without entering the liquid state. Quartz appears in its natural form as the chemical compound, this one. As a product of erosion, for instance, granite, it appears mainly as sand and in practically unlimited quantities. This is a particular property or characteristic that we identify as an advantage or benefit of the optical fiber media. Well, refraction and Snell's law. A beam of light meets a different transparent medium at an incidence angle alpha. This is one media, for instance, the glass, and this is another media, for instance, the air. A ray, or a beam of light, meets the interface of those mediums with an angle of alpha, and that we call incidence angle. One part of the beam is reflected. One part of the beam is reflected. In that case, the angle of reflection is equal to the angle of incidence. The other part of the beam enters the other medium. The other part of the beam enters the other medium. The angle of propagation of the beam changes at this point. This angle, beta, changes. It's not exactly the same as alpha. This effect is called refraction of light. According to the Snell law, the sines of the angles alpha and beta are inversely related to the refraction factors N1 and N2. Using this equation reflect the Snell, the law identified or discovered by Snell. If we apply this, we could see that perhaps when beta is equal to 90 degrees, in fact, we will have what we call the critical angle. Then typically, if the angle of incidence alpha becomes stepper and stepper, one arrives at a situation where the beam of light is no longer refracted into the other medium. There is no refraction. It then runs in the boundary layer between the two media. An angle beta equal 90 degrees with sin 1 results. This special angle is called the critical angle. The critical angle, then the sin of the critical angle is equal to the fraction of the relation with between the two refraction indexes. All angles which are stepper than the critical angle cause the beam to be reflected into the denser medium. This means that total reflections takes place. The critical angle, then, if we respect the critical angle, that is the beam arrives always steeper, then all the beam rays will be reflected in the interface between those media, between the core and the cladding. And then all the beam will be confined into the core of the fiber. Well, then the objective, remember, the objective is that the light that is propagated within the core of the fiber will be confined, will be guided by the core of the fiber. Well, there are typically different types of optical fibers, the multi-mode and the single mode, and typically the multi-mode fibers with step index profile, the multi-mode fibers with graded index profile, and the single mode fibers. Then the multi-mode fibers with step index profiles. In fact, a step index profile, that is the cladding with N2 refraction index and the core with N1. And there is a step between the two medias. The optical power of a light pulse is distributed over multi-modes, that is many rays. In multi-mode fibers, the modes propagates by different paths, that is different modes. Some rays are propagating along the axis of the core, and some other rays are propagated following different paths. A different path. The rays travels by different paths, but all with the same velocity, the same speed, and thus they have different transit times. Therefore, the length of the pulses increases with increasing fiber length. Each time the fiber is longer, the difference of the different paths is higher. then the pulse will be deformed proportionally to the length of the fiber. This type of fiber is employed only for short distances, very short, less than 100, at low data rates. Moreover, today this fiber type is not employed anymore. And remember, multi-mode step index are one of the first fibers, but nowadays that kind of fibers are not employed. Multi-mode fiber with graded index profile. The graded index profile of the core is achieved by many layers of glass, where each layer has its specific index of refraction. These indexes decrease gradually from the center toward the cladding. That is, in the center we have a refraction index N1, but this refraction index will decrease until the cladding. Then there is what we call a graded index profile. This is the profile. This is the profile of that kind of fiber. Is different from the step index profile. And due to the continued change of the index, the refraction index, the rays are refracted constantly when crossing the borderline between the various layers. The rays oscillating around the fiber axis still travel a longer path than the light rays along the fiber axis. However, due to the lower refractive indexes outside of the fiber axis, these rays travel correspondingly faster, and then the result is that the delay time difference of the various rays disappears almost completely. Then the bandwidth of the multi-mode fiber with graded index profile is higher than the step index profile multi-mode fibers. Pay attention that typically the multi-mode fibers has a core of 50 micrometers, and the cladding with the core has a diameter of 125 micrometers. The multi-mode fiber with graded index profile, due to the difficult manufacturing process, the fiber is relatively expensive. Therefore, today it will not be employed for long distances. The relatively wide core diameter provides good launching and receiving conditions. Thus, the main application for these fibers are the local area networks, where short distances have to be bridged. This fiber type is specified by the recommendation ITU-G recommendation G651, and two types are standardized: the type A with 50 micrometers core diameter, and the type B with 62.5 micrometer core diameter. The single mode fiber, even in high quality graded index fibers, a certain delay time caused by the various modes is still present. If the diameter becomes smaller, then only a single mode, the fundamental mode, can propagate in the core. Such an optical fiber with only one mode is called a single mode fiber. These fiber types are specified by the recommendations G652, 53, and 55. Pay attention that the main difference between the single mode and the multi-mode fiber is the core diameter. The core diameter is typically of 8, 9, or 10 micrometers. And the profile is a typical step for profile index, like this one. Well, then we explained the difference between the different types of fibers, the difference between multi-mode fibers and single-mode fibers. The difference, remember, is the diameter. The core diameter is lower in the single mode fibers, and that permit to propagate only one mode of the beam light, and this is the characteristics of the transmission medium that permit to reach higher bandwidth. Well, in order to then to transmit information with light in the transmitter, the electrical signal is converted into a light signal in an electro-optical converter, typically a LED, that is a light emitting diode, or a laser diode. To be more precise, the light intensity of the transmitting diode is modulated by the binary pulse modulated diode carrier, that is this current, and the light with the power P is coupled with the optical fiber. This is the light emitted by the LED or the laser diode, and the light then is propagated across the optical fiber and is received at the receiver side. After traversing then the optical fiber, the light is converted back into an electrical signal in an optoelectrical converter, typically a photodiode, at the end of the transmission route. Well, when the beam of light is propagated in the fiber, in fact, the light is suffer an attenuation, and the attenuation could be measured in units of dBs per kilometer. This is the function. We could see here the function that relates the attenuation based on the wavelength of the light. And typically, we exploit three bands or windows of particular wavelengths. This is the first window, this is the second window, and this is the third window. Then remember, the first window is the 850 nanometers band. The second window is the 1300 nanometers band, and the third window is the 1550 nanometer band. Pay attention that, for instance, if in those windows the attenuation is lower than in this one, and those windows are appropriated, for instance, to be used in longer links of fiber. Fiber optic cables. Fiber optic cable, also known as an optical fiber cable, is an assembly similar to an electrical cable, but containing one or more optical fibers that are used to carry light. The optical fiber elements are typically individually coated with plastic layers and contained in a protective tube suitable for the environment where the cable is used. Different types of cable are used for different applications, for example, long-distance telecommunication or providing a high-speed data connection between different parts of a building. Here we are some pictures where we could see that kind of optical fiber optic cables. Each cable has, in fact, the optical fiber, but is protected with different layers. The typical cable with the connectors, and there are several different types of connectors, of fiber connectors. Then in this table we could see typically some cable types. There are different cable types that we could use. This is the core diameter. This is the cladding diameter. And there are different, those cables are multi-mode and those are single mode. If we use, we could use the cables at different wavelengths, and depending the wavelength, we have different attenuations per in units of dBs per kilometer, and typically those are different kind of remember this, the electro-optical converter that could be LED or a laser. Then, depending on the electro-optical device, that could be a LED or a laser, we could work at different wavelengths, and typically we could reach different distances. For example, in this table, we could see the use of different fiber, the different fibers, fiber cables that we list in this table. For instance, to be used in different links, Ethernet links, for instance, to be used in gigabit Ethernet, 10 gigabit Ethernet, or 40 gigabit Ethernet. And the different distances that we could reach at each bit rate. Pay attention that, for instance, we could use the same cable to work at 1 gigabit or at 10 gigabit, but the difference always is that there is a limitation that we could call bandwidth distance product. 1 gigabit per 300 meters, 10 gigabit per 30 meters. There is a limitation. That is, we could reach longer distances, but with lower bit rates and vice versa. And this is a chart in order to identify different frequencies used in different transmission medias. Typically, for instance, remember in light we work at in the order of hundreds of terahertz. Those are typically gigahertz, that is microwave frequencies. And well, in order to be to relate the different spectrums used to transmit information.